呀，不是不是欸那个一个卖那种家具的店。然后他上当时我的4个企业是这样哦，那这个啊，
或者一到13了。
我不一样啊，它的后面的形状没有，它下一个人呢不太一样。下一个人呢，你越拿我们第一个就是什么？一个没有完全对，所以就都可以。
这是一层，我还是谁是他的案子啊？就是，然后再一次他的案子，一次案子出来嘛。
这样，这样子没有。
啊，我是想看
这种是
是竞争加10点到，
啊哦，他也是有听，哦，吃错东西，吃错东西啊，
对，是不是？
来
就是
啊，我懂了，我懂了，他的昨天理念没有做完，肯定是，那就不是，那就能，
我不行，
他一定没做完了，还有他昨天多聊天，对不对？
这我不认识。
昨天都累了，自己不要找自己的事情，把它丢出来。我昨天都累了，说没电，累了，我累了去。
就来那个，可能
解完电，
我要去的这东西，然后还在吃饭，你在做这个事情，你在去死啊！那天气那到我很天很气温，那个说是不是可以等很久啊？一个点没有，没有，还可，因为我真太多个丢一百，我自己换衣服，每次你把那个去换衣服，我那个枕头这里放在这里，而且我都弄了很大，好运。我那个我跟你说，
他有一点是那个吧，这样的情况，这一点还是一点，
没有了呀，就在前那个
把导那个就一个然后加嘛，但是照样都最开始不一样。
对，大家，
有时间是可以来讨论这些问题，有时间自我感觉，嗯，
看我，你这么我说这样，我跟你讲，然后就教一个，那你等你教完一个，我怕0.12点是，这样3点对3点对的，对， 来的。
Hello，现在多2分钟。
还在看你的 blog
喂，vlog 几分钟 vlog？
我是一个听他讲话。
等下break 的时候可以歇一下。
就冰箱开微信。
给轮流。
你忘记我我连订都没有，被我换点差点。对，我要我。做出来很久了，那个 video。还做了1分钟报。好，有几分钟？差现在手机，我手机。我 Xbox 我的，你看看10分钟，我也帮你算没错，我上 YouTube 来做，不到影片原本还有延迟的影片。我手机你看它不叫 box， 对，这可以点的时候写放个 box， 放个 box， 看可以看到是我给它的另一个对是的。然后我拿出来，然后放一个自己一下，然后我的 Xbox 出来，30分钟，我放进 YouTube 还有其他20分钟。我们那电脑哇，电脑浪费，因为你存个电脑得10秒，30这样子哦，你讲的越慢，那个越慢，还是我转，我觉得说很快，因为我一打进来，没有我这对你讲，那我来听看，他为什么要这样子打？然后呢，我在看你讲，我给你自己打点事，就刚做完，我有算。自己去上来3次的话，就会相差随便点40多分。要是那天两天，我被什么？对吧？或者讲我的话，我说太忙了。对吧？而且那个两次没这样，一个题目，很好，这个。Start. Okay, this one day I went to shopping and furniture shop, and then I saw this tag here. I find it quite amusing. 3-dimensional pillow. And then I go and see what's the 3-dimensional pillow. And then I think about it. Isn't it all pillow are 3-dimensional? 是吧？对不对？啊，不是全部 pillow 都是 3-dimensional。Oh, this 3-dimensional price at almost 300. 他的意思是啊，他3-dimensional的意思，good point, good point. So the basis here is softness, elasticity, and fragility. 对啊。OK， yeah， 就看到一个很好笑的东西了。OK， yeah. Before we start, so we have 2 more lecture to go. Last question in your assignment. Maybe you can try first. If you really cannot, then maybe you can extend time. Because I'm not sure when I'm gonna get to that topic, either today or next Friday. Because our class are like at the end of the week, so pretty hard to manage. You can try and read advanced first to do the assignment question. It's just a computation. So we start with new material. Let's recall some important concept here. So which is vector field and a scalar field. Okay, so let's look at some examples. Vector fields. Vector fields, let's look at function from R2 to R2. And then scalar field. What's the thing that differentiate vector field and scalar field? The codomain. Okay, so usually when we talk about scalar, we refer to the codomain being the scalar, and then vector field correspond to the codomain being the vector space.
Actually, both of them are vector space, if you realize. Okay, but scalar usually only fixed for the how to say, scalar only fixed for like real number, complex number, that kind of thing. Okay, vector we can go higher dimension. Okay, so how we visualize these item here? Visualization. Okay, how do we visualize them? So, for function from R2 to R2, your domain is a R2. Okay, so sorry, shouldn't draw this. So it should be XY. And every point on this domain, what do you attach? You attach a what's your codomain? You attach a R2 to my two-dimensional vector here. Okay. But in scalar field, right? Your codomain also R2, but what do you attach instead? What's your codomain for scalar field? Huh? What's your codomain for scalar field? R, right? So meaning you attach what? A real number. Okay, so you just attach number on top of these point. Okay. Okay, no? Yeah. So do you think that this function is natural in space or not? Do you think that it's natural in space? When can you use them? Like for example, vector field. When can we use them? Then maybe you want to describe like what this point will move after a time t. At this point we're going to move after a time t. And then on this space, when you attach a number to a point in space, what kind of number you can attach? In real situation, real world situation. For example, I can measure at this point, what's the temperature? Right, maybe every point in this room has different temperature. Okay, so temperature distribution is a scalar field. Okay, no? Temperature distribution. Right. Okay. Okay. Yeah. Any question about these two objects here? Okay. So today we're gonna go into Green's theorem. Green's theorem. So before going into Green's theorem, we want to define a positive orientation on a simple closed curve. Still remember what a simple closed curve means? Closed curve means what? Okay, it forms a loops. Why it forms loops? Because the starting point and the ending point is the same. Simple, eh? Right? No self intersection. Okay. So for example, this kind of loop is not closed. Okay, because got a self intersection here. Okay. Okay, got a self intersection here. Okay. So what's the positive orientation here means just says that the orientation on this curve is counterclockwise. Okay, so for example, this curve here, the orientation is counterclockwise. Okay, counterclockwise. Then on B, this orientation here is negative orientation here. Why? Because it is clockwise. Okay. Yeah. So you see our orientation, positive orientation here also matches up with how we draw XY axis. Right. We draw X on the horizontal axis, we draw Y on the vertical axis. So X to Y is a counterclockwise. Okay. So this is the contention. Okay. No? That's why we call it positive. This is how we draw XY, right? You start with X and then go to Y in the counterclockwise. Okay, so this follows how we draw XY plane. Okay, and another thing is if you have a closed loop, right? Simple closed loop. That means what? That means you will bound a region here. Okay, you will bound a region here, and then we call it D. And if we fix our curve to be positive orientation, okay, imagine you are walking on this curve here. Okay, you are walking on this curve here with a counterclockwise direction. So let me draw you like this. Okay, so this region, right, you will see that it is always on your left or on your right. On your left or on your right. So you are walking around this curve. So there's a leg D. So this leg is always on your left. Okay, this region here is always on your left. Okay, later you will see these concept pop up when you try to do integration. All right, so what's Green's theorems here? So let's see the positive oriented, so meaning counterclockwise, piecewise move, okay, so it's differentiable. So this one is infinitely differentiable. Infinite differentiable. And simple closed curve that forms a boundary of D. So D is always on your left side in the xy plane. So let's draw this condition here. Okay. If Pxy and Qxy have continuous partial derivative on an open region that contains D. So open regions means what? There's another open set. There's another open set here that contain D. Then what? And if you do double integration over D, okay, of this, maybe this combination seems weird to you now, okay, but later we'll see why we set it like this. So double integration of partial Q over partial X minus partial P over partial Y dA is equals to the line integral, okay, over C P dx and Q dy here. Okay, something to note here. Okay, something to note here. So if you look at the right hand side here, we match P with dx, okay, match Q with dy. But on the left hand side here, we differentiate Q with respect to x, and then we differentiate P with respect to y. Okay, so there's a purposely done. We swap the variable here, and we introduce a negative sign here. Okay, later we'll see why this makes sense. Okay, but for now, you can memorize it. The opposite signs or opposite variable on both sides. So what's the strength of this Green's theorems? On one side, you have double integral. On the other side, you have a line integral. Okay, so you relate line integral to surface integral. Okay, double integral. Okay, so meaning if you want to compute something in the region, it's equivalent to just compute an integral on the curve that bounds this region. Or if you want to calculate a line integral around this closed loop, you just compute the surface integral inside. Whichever one is easier. Okay, whichever one is easier. 我意思说你要算左边就得用右边算，要算右边可以用左边算。Okay. Okay, so sometimes you'll see this notation here. If you are computing an integral over a loop, so it tells you you are doing a loop integral here. Okay, if I put a circle here. And also, automatically, we will think of that curve as a positive orientation. Okay, already chosen. Do you know that there's a difference with positive orientation and negative orientation? Right. Last time we talked about, you need to parameterize differently, right? These two curves. For example, let's say this is a circle. So let's say x equals to r cos theta, y equals to r sine theta, where theta go from 0 to 2 pi. Then how do you parameterize a negative oriented circle here? What do you need to set? S equals to minus r cos theta. And then you can fix the same y here. Okay, so then you change the orientation already. Yeah, not. Okay. Yeah. So automatically, when we do this loop integral here, we will assume positive orientation. Okay. So let's look at example how to use this. Okay. So let's look at this question here. So let's see be a boundary of a triangle with vertices 0, 0, 1, 2, and 0, 2. Calculate the following loop integral here. So there are two ways to do it. One is a direct method, B is a Green's theorem. Direct method means what? You need to parameterize your curve. Okay, so you need to parameterize your curve. Second, it says that use Green's theorem. But what's the condition of Green's theorem? It has to be a loop integral. Okay, so can you see that this C is a loop? This C forms a loop. Okay, so the starting point, ending point is the same no matter where you start. And it bounds a region on the left, okay, of this curve, considering the orientation. And this curve is also simple. Okay, there's no self-intersection here. Okay, there's no self-intersection like this. Other than the endpoint, which is not here, right? That's on Wednesday. Okay, so self-intersection means no self-intersections means no self-intersection other than the endpoint. Okay, obviously you have to intersect the endpoint here, otherwise cannot close. Okay, but it is a self-intersection around, not at the endpoint. We count it as a self-intersection. Okay, right. So let's do the first method first. So let's parameterize this curve. So how to parameterize this curve? You do it at once. You do it at once. So how are you gonna do it? So we split this curve into three parts. Okay, so we split it into C1, C2, and C3. Which curves is easy to write down the parameterization? What do you think? C2 and C3, vertical and the horizontal, easiest one. So let's do C2 and C3 first. So horizontal. So what is your X? What is your Y? Horizontal means what? Which one is fixed? The Y coordinate is fixed. So Y coordinate here is always 2. Okay, but X is changing. So changing, you can do it linearly, right? So just let your X to be T. Okay, and then let T run from 1 to 0. Is it 0 to 1? If you set T as 0 to 1, is this the orientation you want? Okay, so let X to be minus T and then T from minus 1 to 0. Okay, so let's check. So when T equals to minus 1, my X is 1. Okay, and then when T is equal to 0, my X is 0. Okay, so I start with 1, 2, and then end with 0, 2. Okay, good. Okay, so this orientation is correct. And then what else? C3. So what is the fixed variable? X is fixed. Okay, Y, similarly, you can let it to run linearly. You want to parameterize other way also can. You want to, yeah. But make sure that your domain is correct. So where's the domain here? Let's say going to 2 to 0. Is it correct or not? -2. Again, shift your y equals to -t and then start with -2 to 0. So let's check. So I start with 0, 2. What do I get? 0. If t equals -2, I get y equals to 2. Okay. If t equals 0, I get y equals to 0. Any question? 有问题吗？有问题吗？还是你要问为什么我们不要放 y equals to t？啊，可以啊，可以问啊，可以问啊。好，如果你要放 y equals to t，your domain 呢？From where to where？0到2。Okay, if you put this, where do you start? You start with t equals to 0. So meaning you start with 0, 0. Then where did you end? You end with 0, 2. So you have an opposite orientation here. Okay, so we're trying to swap the orientation. Okay. Make sense? Okay, usually to swap the orientation, you just put a negative sign to the origin. Transition. Okay. How about C1? How to find C1? How to find C1? You could start with finding the line equation of this line segment here. Okay, so what's this line equation? We need to find the gradient, right? So gradient is 2 minus 0 over 1 minus 0, say. Okay, so it's 2. Okay, so this line actually is y equals to 2x. So if you fix your x to be t, then your y will be 2t. Okay. Where's your t range from? T equals to 0 to 1. Okay, so let's check. So after you write down the parameterization, right, check whether you get the right point or not. Okay, when t equals 0, you start with 0, 0, good. When t equals to 1, you end with x equals to 1, y equals to 2. Okay, yeah. Okay, so we have spent time doing this parameterization here. So we are ready to compute the line integral. Okay, actually, this topic, the hardest part is not about the integral. Hardest part is how to get this parameter. Yeah. All right. So this C here is equals to what? C1 union C2 union C3, and they intersect in finite point. So meaning what? You can split out the integral, okay, by the additivity of line integral here. So you can do integration over C1 for x cubed y dx plus 2y dy plus integral of C2 for x squared y dx plus 2y dy, and then plus integral of C3 for x squared y dx plus dy. Okay, right, but you see, my parameterization is in T. So the question you have to do integral over x and y. So what do you need to do? This is a bit like the integration by substitution, right? Integration by substitution. You have x in t. Okay, you have to differentiate with respect. You want to change your integral with respect to x to t. So what do you do? Let's do the first one first. Obviously, you change your x integral from 0 to 1 for x part, and then you substitute your curve into your function. And then what happened to dx? If you do integration by substitution, what do you do? Dx becomes x prime t times dt. Okay, so this is how we get the formula. So x prime t is 1 in this case here, and then multiply by dt plus 2y, so 2 times 2t, And then what's the y prime t here is 2 times dt. Okay. Okay, can you continue substitute the curve into your function and then try and get the calculation done, and then we can check solution together. Give you 2 minutes. Okay, so when you do this substitution, it means what? It means that you are evaluating the scalar function on what? On this curve here. Okay, on the curve. Done。有人算到什么答案吗？来 try 一下，算到什么答案？10 plus 3/8这样子啊，10加3 8分8/3，这么大呗？你呢？你算什么？你算到什么？你算到什么？你讲给我。-2，就这样。OK，还有嘞？还有什么其他答案吗？来看看，讲看看，还有什么不同答案吗？我全部都不懂，不是要再算一次啊？还有吗？还有其他答案吗？n 次哎，-2/3，我也是-2/3啊。可以 check 一下吗？哪里错掉？Should be -2/3 if not wrong。啊，你算到了啊？OK，还有嘞，其他人算到了吗？-2/3，我没有算到，check 一下哪里有错吗？小鹏呢？啊，还没算到。OK，算算看，围棋那一桌要有人算到吗？你算吗？负2/3，OK，-2/3。有问题吗？有 check 到自己哪里错吗？ 我试下写第二排出来啊，看一下，t square 2 times two times 0. Oh, so this part is 0. Actually, the last two is easy to compute, right? One of the sum is 0. Okay, one of the sum is 0. One of the sum and the sum is 0. And plus one more term, integrate from -2 to 0 of 2 times minus t times -1 dt. Okay, so be careful. There's a lot of minus sign popping. Okay, then you left with the integration. Actually, 如果你们可以写到这个 step， 其实你已经可能超过一半了，超过一半。后面如果算错，或者最后算错 ，maybe call it half. Actually, main part happens when you do parameterization and also how you substitute the curve into your function. 这些做对其实就对了，后面只是计算吧。OK 吗？OK 啊，OK good. So okay, we haven't quite done yet, right? We have part B, which we are trying to use Green's theorem here. Let's try and use Green's theorem. So let's repeat this page. Repeat, duplicate. Repeat this page. Okay, so what's Green's theorem? Let's recall. So recall Green's theorem. Okay, Green's theorem says what? The surface integral of D, okay, bounded by this curve here, of dq over dx minus del p over del y dA equals to the loop integral of p dx plus q dy. Okay, so now you need to match to your line integral. What's your p? What's your q? What's your p? For x squared y, and then your q is 2y. Okay, so let p equals to 4x squared y, q equals to 2y. Okay, and then you want to compute this line integral, you simply just need to compute the surface integral d of del q y. So my q become 2y. So you can immediately see that this is a 0 term, right? There's no x inside there. Minus del p over del y for x squared y dA. Okay, but how to do surface integral on this triangle? Do you remember or not? You still remember the double integral? How to do how to give the integration domain here? So what's the condition on your xy? X going from where to where? So what's the main thing inside multiple integral? The Fubini theorem. Okay, Fubini theorem tells you what? You can integrate without what? Without looking at the order. You can do dx first and then do dy, or you do dy first and then you do dx. So you fix one. Which direction you want to fix? Maybe let's fix direction first. Which direction you want to fix? Dx over dy or dy over dx? Let's say we do dx dy, meaning what? We need to, okay, so let's move this d down first. Any place to write? Let's move it. before this line integral. Okay. Oh, yo, too far away. Okay. So why got a prime here? Okay, so if we do dx dy, meaning we need to check the outermost variable first. So y is ranging from where to where? We need to make sure that this range is a constant. So in this case here, you'll see that the y is going from 0 to 2. Okay, from 0 to 2. But if you fix your y, y how to fix that? Fix like this, right? Okay, if you fix each y, how is your x changing? Okay, let's say your y start from 0. So your y start from 0, this point here. So your x is also just 0. Okay. So when y equals 0, x is going from 0 to 0. And when y equals to 2, your x going from where to where? From 0 to 1. Okay. And then you can see that this x region here will increase, okay, until you reach y equals to 2. But how to increase it? How to increase? What is the lower bound? What's the upper bound here? The lower bound of x is what? 0. How about the upper bound here? Just now we found this line equation, right? Y equals to 2x. So meaning x is bounded by y over 2. Okay, good. So how do you do this integration here? So you integrate x from 0 to y over 2, integrate y from 0 over until 2. Okay, so you do this calculation here. Do you get negative 2 over 3? Okay, let's quickly compute this. Minus 4 over 3 cube. 21. That's 4y cube over cube. So here cancel, get 1 dy. And then you get 6 dy. Here become minus 4 over 24. So d, we got nothing already. Okay, you see this last term is exactly FTC, right? Here, this is FTC. Okay, fundamental theorem of calculus. What do you get? 44、44、44、32。Is it 32? Is it 32? 16 only. Okay, good. 16 over 34. And then you simplify, you should get 2 over 3. Okay. Okay, so these two ways will compute to the same number. Okay, okay. So let's do one more question. Let's do one more question before we take a break here. So let's do this question. Again, you calculate a line integral of this form. So this is, what form is this? This is a p dx plus q dy form over a circle. Okay, over a circle here. So the circle here, it doesn't tell you the orientation, right? But what's this circle? Center at the origin. Okay, so center at the origin with radius 3. Okay. It doesn't tell you the orientation. What orientation you should take here? Positive. Okay. Positive means counterclockwise. Okay. Positive means counterclockwise. So can you use Green's theorem and compute this question here? Okay, try and use Green's theorem to compute this question. And let me know what's your answer. So this is a simple closed curve and smooth. You know how to see this is smooth, which you know how to see this is smooth? Don't know. Smooth means what? 什么？什么？什么？顺滑？不是宣布诶。Smooth here means infinitely differentiable，就是可以无限的那个 differentiate。Okay, infinitely differentiable. So how do you see this infinitely differentiable thing? How to see it? 怎样看得出来它是可以 differentiate？怎么看？啊，小鹏不会，怎么看呢？I mean, well, I mean, you should write this circle as a function first, right? So how to write this function circle as a function? One kind of function you can write down is the vector function, right? The parameterization. So if you try to parameterize this curve, how do you parameterize this curve? S equals to what? S equals to what? T? T, Why? So you want to parameterize circle, right? So what should you use? Polar coordinate, right? So x equals to 3 cos theta, y equals to 3 sine theta. So theta going from 0 to 2 pi. All right. So this is just parametric equation, right? You can write it as a vector function. So what's the vector function here? You just write it as a vector form. Okay, so your x part is 3 cos theta, and then y part is r sine theta here. Okay, so we're asking whether this vector function is infinitely differentiable or not. So if we want to differentiate a vector function, what do we need to do? We need to differentiate term by term. Okay, each coordinate. Is it infinitely differentiable? Can you forever differentiate cos theta? Can you forever differentiate sine theta? Never. You differentiate cos, you get sine, you differentiate sine, you get cos, cosine, 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 cosine. So you just look between cos and sine. Okay, non-stop. Okay, so it's infinitely differentiable. Okay, all right. Okay, so let's write down, see if you compute the right thing. Okay, so if we're gonna use Green's theorems by Green's theorem, so make sure when you do this kind of question, if you use any theorem, write down what theorem you use. Okay, don't straight away compute. Write down by Green's theorems. Okay, we change this line integral into a surface integral. Okay, and what's the function you differentiate over? So del x on 7x plus square root y to the power 4 plus 1 minus del y on 3y minus 4 to the sine x dA. Okay. What's this? What's this? You get 7 minus 3, which is a constant. How to integrate over a constant? Anyone know? How to integrate over a constant? You can use the scalar property to pull 4 out. You are integrate over 1. So if you do surface integral over 1 means what? This represents the area of the domain. Okay, so your domain is what? Is a circle. So what's the area of a circle here? 9 pi, how do you compute it? Pi r squared. So you get 36 pi. Okay, let's say you forget this. You forget this rule here. You forget it. So you go and do your multiple integral of d. You know how to do it or not? how to describe this how to do multiple integral on D here 怎么做跟我讲讲看 or maybe you need to choose coordinate first. You want to do it on Cartesian coordinate or you want to do it on polar coordinate? This shape is a circle, right? So which coordinate is better to do? Which coordinate? Polar. Okay, so if you choose polar, what do you need to choose? D equals to what? So how many variable here? R theta, right? So R ranging from where to where? Theta ranging from where to where? How to describe a circle? This, huh? Radius need to go from 0 to 3, and then theta 0 to pi, 2 pi. Okay. Okay, so you take everything inside here. Okay. And what's the change of variable here? What's the Jacobian? Got Jacobian or not? Let me use this calculation. So here is dr d theta, right? So what's the Jacobian here? Got Jacobian or not? If you do polar, you got an extra r here. Okay, and then your r is from 0 to 3, and then 0 to 2 pi for theta. Okay, so what's this integral? R squared over 2 from 0 to 3 d theta equals to 4 2 pi over 9 over 2 on theta, right? And then you get 4 times 9 pi. Same answer, 936. Okay. Let's say again. 我忘记 polar 了，我只会用 xy， 做得到吗？做得到吗？什么？什么？要分开来，对，没有错。If you consider xy, you need to somehow split your upper bound, lower bound here. Okay, because there's no single xy function can describe the whole circle. You need to split it to what? Upper triangle, upper semicircle is what? The function for upper semicircle here. Y equals to square root 9 minus x squared. Okay, and then bottom y equals to minus square root of 9 minus x squared. Okay. Depend on how you want to split it up. You want to split it to top half or bottom half or left half and right half. Left half and right half, x equals to square root 9 minus y squared. And then the other side, x equals to negative square root 9 minus x squared. I don't think you want to do that integration because you need to get into like trigo integration because you involve square root already. But involving trigo integration is exactly doing the polar integration. Okay, it's exactly doing this. Okay. All right. So we calculate using Green's theorem. So as an exercise, you can go back, try and use this parametrization. Okay, plug this parametrization into here. Do you still get 36 pi or not? Okay, you can do it using this parametrization. Okay, train your line integral. Okay, see if you get the same answer. I got solution here. You can check. Yeah, I will put a solution. You can check later. Okay. Yeah, I even have a past year student solution. Okay. Yeah. Any question about Green's theorem? Later we'll generalize Green's theorem. Later we'll generalize Green's theorem to Stokes' theorem. And then we will tell you why you need to sort the variable when you do partial derivative, and then why there's an extra negative sign there. Alright, so let's take a break until 10:03.
然后computer 这边的 area 就是找对computer 这边 area 嘛，这样的话，
这个 integer computer 这个的 area，computer 这个的 area。
这个 P 跟 Q 它是这边是吧？还是
没有 P 跟
什么意思
Q
啊？
就是 define 在这个 open set 只是应该是这个 proof 的一个 technicality 来的。其实你在算的时候，其实都没有看这个 open region 的，但是你的这个 pxy qxy 只是说它是一个 function define 在define 在整个地方，
整个地
要不要整个地方呢？应该整个地方可以吧？至少在这个 open region 就是 define 吧。
就是这个东西，它是要在它的那一边是吗？还是
没有啊，整个啊，因为它不管是 curve 或者 region 都是在 R2里面，所以这个东西就 define 在 R2，至少要在这个 open region 上面。
对呀？它的意思是东西它是一个function嘛，
对，
它
其实它是一个 scalar function。scalar field 这两个都是。
所以它就是一个 area 在它上面的那个东
我
西。
觉得要写的啊。你讲完了，你讲完了。
我们算的是它上面的那个。
你讲完了，你没有讲完了。
就是这个 volume 哦，因为我们这样，如果是这样看的话，感觉就好像在算那个这个东西上面的 volume 这样子。
哦，你讲这个啊，你讲这个哈，对呀，没有错，没有错。
所以它等于，它就是这个我不太懂，就是
word done 有一点类似 word done，它是撑开来的 word done。
一个
上面
在任何的那个点。
哪一个？
这个 P 呀。
P 对 P，这个有一点像打开，这个有点像那个打开的 word done，意思说你绕这一个圆圈做 word done，其实就是好像里面的一些，像你讲的 volume，对，它是这个一个概念。
一开始我还以为说这个 P 它就是原来所以这个 P 它是define全部
啊。
哦，
这个 xy 吗？R2 吗？至少要在 open region 上面。
所以它表示的
就是你在这绕着这个圆圈做功的时候，其实它跟这一个算出来的一个，我想一下啊，对，
是一样的，
是没有错，没有错。慢一点你会看到为什么。
我懂那个做工了，就是因为如果是做工，它就是那个工对这个区间它 contribute 了多少，那个就比如说好像因为它是 inner product 对吧？所以就是他弄下
来，
就是怎样讲啊，就是
弄上去，弄在这条课上面。
我们的课是这样的，那的 vector field 是这样的。
OK，对，我觉得你这样想是 OK 的。
可是我也是这样想，就
我觉得你这样想是 OK 的。
这个东西是这个，就是跟那个概念是一样的。可是那为什么它又是 define 那全部的那个 region，就很奇怪。
为什么 ？I mean，不是，I mean 就纯粹一个 vector field define 在。
我讲这样总是讲，就是它这边全部弄出来的那个就是它每个不是可能有一个 velocity 在那边固定着，就不要讲 velocity 啊，就是有一个数字在那边，然后它走过嘛，然后它走过全部加起来等于它这边上面的 volume，我是这样想的。
我觉得你这样想没有问题啊。
没有问题。
没有问题啊。
可是为什么他又讲说 define 整个 region，我以为说这两个就是 define 在这
I mean，它整个 region 都有嘛，只是说你走在这条线的时候，你是遇到哪一个？也
OK OK，谢谢。
没有冲突啊。
OK，好好。
对 OK。
你姓郑。所以老师罚球。
那是哪边吗？
然后3%就是
那个
放第30。
做，不行。你们不是讲要 share 你们的 vlog 吗？
没有，
啊，学一下，学一下。
他只回一步就变黄。
是，我帮你先查。
我的那个是马的，知道。
要开 YouTube，要开 YouTube 频道，
已经开去了，我们看了那个 post 的片。
跟我讲好办吧。
我看这里。
我在看。就是你的 Instagram 里面放多的东西。 这个卡，这就是
对吧？我是蓝色可以。你都用算那个，我去年算，
那个差不多，
一算了，
那个在微信了，
你怎么弄？那个说。
我说一直上那个是0103，就大概2.04，然后上面换点红。就是。
我差不多。再数一下你那个数，我要是对不对？这个对出来了。
都成。
这是爱丽丝，
还有这东西，
这个是现在是
X，
这个是到这个
是吧？
主要这两个，
我看一个X1啊，除以
等你，
X2嘛，对，
然后你都要不到是，
这个我那一个是什么样？我觉得按，
哎，我介绍那个那个，我明白那个，Okay, yeah, if you look at three things you have learned before, look at this cow here. So first is a sum, so it's a discrete cow. Integration is a continuous cow. And then the last one you learn is line integral, so it's a vector field cow. Vector field cow here. Okay. So how to see the line integral just now as a vector field? So if you look at this PDSQDY, you should see this as very familiar things. Okay, if you set your F, okay, your F1 to be P and F2 to be Q, this is a vector field. And what is PDSQDY here? Actually, you are dotting your F with your TI. Okay? So meaning you are doing work around that closed loop is equal to some volume that the curve bound. Okay. Just doing work. So how should you imagine this? So you have a vector field Okay, you have vector field, and then inside the vector field, you walk in a loop. Okay, you work in a loop. Okay, so this is your work done. The force time displacement. Okay, this is your work done around the loop, but it is at the same time equal to a volume. Okay, or the multiple integral over the region you bound. Okay, but the vector field that the scalar field that you integrate over is this weird thing here. Is this weird thing? What is this? What can you think of it? What's this weird thing to represent? Do you have idea? Maybe you can try and think about it. Later I'll tell you what's the answer. Okay. While you're doing work in a loop, okay, it's equal to some double integral of some scalar function. What is this scalar function trying to say about this vector field? Okay, so before we go further, let's do a few more questions on Green's theorem first. So I think this one we can skip. Let's skip this now. Okay, maybe we just quickly discuss and we don't calculate this. So let's say so you want to do this line integral. Okay, this line integral is a loop integral. So whenever you see a loop integral equation, calculation, you should think about Green's theorem. Okay, can I use another way to compute it or not? So what's this loop here? So this is a boundary of a semi-annular region D. Okay, in the upper half plane, bounded between two circles. One circle is with radius 1, and the other circle is with radius 2. Okay, both centered at the origin. So this curve is what? Simple and close. No self-intersection, right? Okay. So simple and close. So you have tried to use Green's theorem here. So if you're gonna use Green's theorems here, you need to decide what's your D. Okay, can you describe your D or not? Now you turn the question on line integral to double integral. Okay, so double integral, you go back to a previous chapter. So how you decide your D? Okay, so how many ways to do double integral here? You can use Cartesian coordinate or you can use polar coordinate. So which one you want to use here? Polar, right? Because it's like a circle. Okay, so if you're gonna use polar, you need to determine where is your r, where is your theta. So where's your r, where's your theta? Your radius from where to where? To get this d here. 1 to 2. Okay, radius is going from 1 to 2, correct or not? 1 to 2. And then your angle, 0 to pi. Yeah, because it is only at the upper half plane. Okay, 0 to pi, upper half plane. Then you do this multiple integral. Okay. Yeah. Okay, now. So you can use Green's theorem to compute line integral in terms of double integral here. Okay. Later we'll call it surface integral. I just realized I didn't tell you there's another name for it. Because of we call this as a line integral, right? So this becomes a surface integral because you integrate over a surface 2D. Okay. So far, okay. Okay. So let's continue. And actually, Green's theorem can do more than closed region. Okay. Or yeah, closed region. We can apply to the region with pole actually. Okay. That is the region that are not simply connected. Okay. Not just simply connected region. We also can apply it to not simply connected region. So how do we prove this? So what we can do is we can split this not simply connected region to two simply connected region. Okay, we can split it into two. So how do we split it here? So you can see that this region with hole, right, actually bounded by two curves here. So what they call it? Let's call these curves some names. So let's say the outermost curve is C1, and then sorry, let's see. So okay, let's call the outermost curve C and then the innermost curve W. Okay, so C go in the counterclockwise direction, W go in the anti-clockwise. Okay, later it will make sense why we do it opposite way. Okay, so how do we split this region into two simply connected regions? Okay, if we split it into two simply connected regions, it is what we had in the Green's theorem. Okay, we apply Green's theorem twice. So how are we gonna split this? So to split it, we introduce these two lines here. So these two lines, the two blue line here. Okay. So with this two blue line, right, we introduce two more lines for each. Okay, one going back and one going forth. Okay, so let's say we go from the C line to W at the left hand side using B1. Okay, so going this way and going from W to C using B2. Okay. So actually B1 and B2 is the same curve but with different direction. Okay. And how about the other side? Let's call it should we use different name? Maybe we don't use different names, just use negative B1 is enough. Okay. The other one we call it B2 and then the other side is negative B2. Similarly, we split C into two parts. The top part we call it C1 and then the bottom part we call it C2. So C is a union of C1 union C2. Similarly, we do for W. So W is the union of W1 union W2. So where is W1, W2? So the top one we call it W1, the bottom one we call it W2. Okay. Okay. No? Okay. So in this way, what we have done, what have we done? So what we have done here. So let me write something. So you can see that D prime is the region bounded by a curve starting from C1 union B1 union W1 union B2. Okay, and then D prime is the region bounded by C2 union negative B2 union W2 union negative B1 here. Okay, so you could imagine that I can do a Green's theorem in these two regions. Hey, let me ask you a question. If you do Green's theorem on C1, what happened? If you do Green's theorem on C1, what's the multiple integral you compute? You are computing the region that with the whole field. Okay. And if you do Green's theorem on the inner loop, you are computing the double integral with the whole field also. Okay. So you are not computing the annular region here. Okay. So we're trying to compute what happened in this annular region. So let's see how we do this. Okay. So what do you think? What do you think how we do this new D here? So let's write down. Let's say my D is D prime union D prime prime now. Okay. Let's say we want to do this special scalar function del over del Q over del X minus del P over del Y. Okay, how do I apply the Green's theorem that we know before? Let's say we want to compute this. So that's a whole day. So remember, you see double integral on the union. So what do you need to think about? The additivity of this integral here. Can I split this integral into two sum or not? When can I do it? When can I do it? Partition? When the intersection is what? Finite number of curve. Okay, so you can see that D prime intersect D prime prime on the blue line. Right, two blue line. Right. Blue 它们的 intersection. 就那两条蓝线嘛。Okay, so we can split out the sum. So let's split out the sum. Okay, let's split out this sum here. Okay, let's split out this sum here. So once we split out this sum, then this is the familiar region that we know how to integrate over. Okay, so we can turn this into a integral, okay, by using Green's theorem now. Okay, so what's the clockwise curve that bound d prime here? You find what's the clockwise curve that bound d prime? 有没有看到一个 clockwise 的 curve that bound d prime here? Okay, so what's the clockwise curve that bound d prime? W1, B2, C1, and B1. Okay. 对吗？sorry, counterclockwise, sorry, counterclockwise. Okay. Is it counterclockwise? 对吗？ W1, B2, C1, B1. Is it counterclockwise? Counterclockwise, right? 有吗？有 counterclockwise 吗？ Hello. Okay, Ping Xiong, what's the counterclockwise curve that bound D prime? 喂，我问你 curve，你给我 region 对吧？curve. What's the curve that bound D prime? What's the counterclockwise curve that bound D prime? W2，然后 minus B1, B2, minus B2，这个 bound 的是 D prime prime 啊。他说 D prime 什么 ？W1， OK W1。B2, C1, B1. Okay, good. so this curve is from B1 union B1 union W1 B2. Okay. On P dx Q dy. And just now already Ping Xiong helped to check D prime already. So let's write it down. So C2 union negative V2 union W2 union negative V1 on P dx Q dy. Okay, so actually you realize there's some of cancellation happening here. There's some cancellation of, because we got negative orientation, right? We really can pull this calculation now. So let's don't put P dx Q dy. I just want to put how many curve we integrate over. You can put it yourself. You got negative B2, right? I can make it negative of integrate over B2 because this is the orientation property that the integral had. So what did you see here? B1 and B2 disappear, you see? They cancel out. Okay. So in this picture, what did you see? Actually, you integrate the curve forward and backward. Okay, so actually they cancel out. So in the end, what do you get? In the end, you just get the contribution from C1, C2, and W1 and W2. Okay, so let me draw the picture again for you. So the C1 is going counterclockwise, but the B2 is going clockwise. Okay, so here is C1, C2, W1, and W2. Okay, so you add out what? You add out the counterclockwise contribution of C1, and then you add out the clockwise contribution of inner loop, of the inner loop. Okay, whenever you want to do a annulus calculation. So let's do one annulus calculation here. Okay, let's give this function, this vector field, so minus y plus x, but divided by length, x squared plus y squared. And I want to show that this, this line integral here. So what's this line integral here? So let's be careful. What's this C here? This C is a special C. Positively oriented simple closed path that encircle the origin. So meaning what? So you have a R2, okay, you have any C that encircle the C, and then this integral of this particular vector field here must be 2 pi. How to show it? And then the hint they draw is this one. You need to consider annular region. Okay, the hint is here. So let me directly show you. I mean, we won't test you on this, but I just want to show you how useful is this annular calculation here. All right. So let's ask the first question here. Why this origin pop up in this question? Why they origin here? 又来个00点啊，有00点的出现，你就应该要想一个东西啊，对不对？会不会要被领除？是不是 ？Okay. So can you see that this function is divided by the length of the point, but origin has what length? 0. So if you divide by 0, that means this vector field is not defined at the origin. So you need to make sure that your curve don't pass by this origin. If you pass by this origin, then your integral will not be defined. Okay. But 还有更强的 even stronger result here. If you integrate with over NC that circle around this origin, you get 随便你画. So meaning maybe you can go like a snake. Also 2 pi. Okay, but how to prove it? Okay, how to prove it in general? Okay, how to prove it in general? So here the problem here, I mean the question here is very clever. Okay, this approach is very clever. We don't know about C, but we can control the small c prime here. Okay, we can control the C. Okay, how do we control the C? So this is a very nice C prime here. So let's introduce C prime. Okay, such that this C prime here is parameterized by a circle centered at the origin. Such that what? Such that this circle, right, live inside the region bound by C. So that C prime live inside the region bounded by C. Okay, can you do that? 能不能 always do it? Can you always do it? If I give you any loop that bound a circle, can you find a small circle inside here or not? Can? Not pass through the origin. Yeah, without passing through the origin. Can or not? 能吗？你看一下能不能先，我们再打算这样做。Do you think it is possible? Let's say if you have a C, okay, that encompass the origin, okay, can you always find a circle around the origin that live inside this region bounded by C? Can? 能够吗？参与怎样做？不知道，没有，能不能先？能不能先？可以，你可以，为什么你觉得可以？你要跟我讲，对不对？大概错也不用紧。不知道怎样？为什么直觉告诉你可以？ 看出来的。OK，有人知道怎样吗？会写，会写，你觉得可以吗？啊，OK，这样做。所以觉得他知道这样做。哎，公平。好，确实无限小，但是你能不能够 like 给你一个第一，你能不能够决定一下这个 C prime 的 radius？啊，要不要拿小一点？拿小一点啊，不然它 intersect 了，等一下。Okay, so what you do is if you given a C, right? Okay, you can compute the distance, okay, of every point from C to the origin. Okay, since it doesn't touch the origin, right? 至少都有一个距离 epsilon 的距离的差别。没有呢？ OK，我画一个。So let's take this C 啦，let's take this C in the picture. So you can compute every distance, okay, between the point on C to the origin. Then 这个东西我们可以叫它 epsilon， OK， 可以叫它 epsilon。你肯定可以找到一个最小的 epsilon。And then what do you do？找到最小的 epsilon，you just take epsilon over 2。right? You just take epsilon over 2, then 你就可以找到你的 A 哦。Okay, does it make sense? Okay, so here I will say that exists an A. Okay, in R such that this is true. Okay 吗？有问题吗？Any question？有问题吗？每一个点你都可以算它跟那个 origin 的距离，and then 你就拿那个最小哦，最小的为了避免那个点，你就再除2再小一点，那你已经就不会遇到所有的点了，对不对？I mean, you can use triangle inequality to prove it, but OK，有问题吗？有问题吗？有问题吗？哎，还是你知道我在做梦吗？哎，精神，重复一次。啊，重复一次。先开始讲我要做什么先。OK，不然那个 Isaac 就他的，我要做什么？啊，我要找什么？我要找什么？好了，一个 C，一个 oriented simple closed path that encloses origin 包这个 origin，我要找什么？哎，你给我这个 C，我要找什么？我要找一个 C prime，这个 C prime 是什么？C prime 是什么？啊，C prime 是什么？不止 subset 啊，我还很 specific 的 subset 哦。circle，OK，我要找一个更小的 circle，OK，that live inside the 活在 the region ，okay, bounded by C， 看到怎么找这个最小的？我可以算每一个点在 C 的距离从 C 到 the origin，OK，然后我可以找最小那个 call it epsilon，然后我想找一个包在里面的圆圈，不要拿那些点 that is maybe epsilon over 2 away from the origin， 对吗？其他点都是至少 epsilon away from the origin 嘛，对不对？我拿 epsilon over 2，它就肯定全部都在里面的。Okay, if you want to prove it rigorously, you need to use triangle inequality. Okay, okay, so we call it A here. Okay, we call it A. Then what? Then some more. Then what? Then by what we have deduced just now, what do we have? So 看一下这边的orientation 是怎样的。So if we do the contribution from both what? From both circle here. Okay. Remember that just now when we do this annulus Green's theorem, okay, we need to add the contribution from the outer loop and the inner loop. But we consider inner loop as a clockwise or counterclockwise? Clockwise orientation. Okay, but outer loop is still counterclockwise. Okay, so I put negative C1 here is because on that picture, that C prime is oriented counterclockwise. Okay, so I put negative. So to make it clockwise. Okay, ma? Still remember just now, we need one counterclockwise, one clockwise. Okay. So if we add out these two portions here, what do we get? Huh? So let me see. Let's try. So let my f of xy to be pq. Okay, such that p equals to minus y over x squared plus y squared. Q equals to x over x squared plus y squared. Okay. And what? So recall that the line integral of f dot dr is simply what? The line integral on f, okay, with respect to x plus q with respect to y. Okay, so this is the this is what? This is the Green theorem's form that we need. So if we do this line integral here, okay, this two line integral here will add up to the annular region that we want to integrate. So this part is by Green's theorem. Okay. Okay. So you try and compute this. Compute this. Del Q over del X. What we get is what do we get? Del Q over del X here. Wow. How to differentiate this with respect to X? X over X squared plus Y squared. Integrate. Sorry, then partial differentiate. Quotient rule. Quotient rule, what do you get there? Quotient rule. Then differentiate. Del Q over del X. 这样做。 将 partial differentiate 啊，什么答案？什么答案？negative x square plus y square over y square square. Okay, good. Okay, the other side 呢 The other side should be similar, right? 因为只是 x 变到 y，而且还有一个 negative sign. So what do you get 啊？You get 一样，一样，一样嘛？Symmetric。可是那个 negative sign 没有影响咩？这个 negative sign 没有影响咩？应该要 swap 一个 negative sign 的吧？要不要 swap？一样还是要 swap？这个 negative sign 没有影响哦，没有影响。OK，why？为什么没有影响？它算法发生什么事情啊？已经 swap 了，已经 swap 了，我叫做已经 swap 了。Oh, well, I mean, the question is, you see, without negative sign, you compute negative x squared plus y squared, right? But why differentiating minus y still get the same answer? 一定会有 square, OK，我 square 发生在哪里 ？X 变成 y，我的 x, yeah, sure. So you mean negative y appears inside here? Okay, okay. So where does the negative sign come from? 下面这个 negative 不是，这一个 negative 不是，不是吧？是没？啊哈。
x 下面那 x 可以写成 y 可以写成，还多一个那个 negative sign。
喂，听不是很懂你讲么？再讲一次。把符号搬出来，OK，把符号搬出来也很开心。把符号搬出来哈，Sure，把这边变成加，里面的 y 跟 x 对调就没问题。哦，OK，yeah，OK，good，OK，make sense，，OK，这样也很好，这样很好。哎，有人在跟着吗？在跟着吗？现在在跟着在干嘛？OK。Yeah，这样也可以。OK，but in the end, what did you see? Actually, these two will can cancel。而不管我怎样 parameterize 这个 d 都不重要，因为你 integrate over 零。OK，so you get 0。OK，so what do you get here? Actually, what's the result you get here? So, OK，继续。So you will see that the line integral over c is actually the same as the integral over the small circle that you create. Okay, the small circle that you create. Okay or not? Yeah, the small circle you create. Okay, so because now, 你看这里的好处在哪里 We turn something that we don't know how to parameterize to something that we parameterize. C prime 我们 parameterize 了 C 我不知道，他没有告诉我什么 C，他只是告诉我它是一个 loop around origin。我不知道怎样 parameterize 它，因为他没有告诉我它长怎样。但是 but C prime 是我们选的，我们选 C prime as a circle 我们知道怎样 parameterize。OK， 就是 radius cos theta，radius sin theta。OK， So once we know this, we can plug the parameterization into my vector field. Okay, so what's the vector field here? What's the vector field here? So what's my P and Q? P and Q 帶晒。Okay, so what's the parameterized curve here? X equals to A cos E, and then Y equals to A sine T. Okay, so let's use this. All right, so what we get here, I quickly compute. You can compute yourself, see you get the same answer. No? This one dot with negative A sine T, A cos T. Okay, so you need to compute what is X prime and then Y prime. Okay, to be precise, if you like, it's better to write out what's the function of X. So X depend on T, Y also depend on T. Only then you make sense to differentiate them. Okay, otherwise X prime and Y prime is just a random new variable. OK 吗？有问题吗？有问题吗？Feel free to ask 啊，如果现在卡，你就要现在卡，不要考试才卡。OK， but in the end 啊，what do you get？诶，你会看到哦，它的那个 A 哦不见掉了。It's not dependent on the A you pick. This calculation. Okay. And what is this? What is this? This is just a circumference of a circle with radius 1. Okay. So that's how you get this 2 pi. Okay. Yeah. If you plot out this vector field, can we try and plot this vector field out? So let me plot this vector field for you. Okay, so if I plot this vector field, you see, okay, it is like this. So it's like rotating. Okay, it's rotating. But I haven't divided by the length yet. Maybe we can divide by the length. So if you divide by the length, you are just trying to make all the length vector to length 1. So let's length. Okay, so it's a rotating vector field here. Can you see rotating? Okay, so it says what? The calculation says what? If you do a work around the in here, okay, your work done is always 2 pi. 什么意思啊？什么意思哦？不管你不知道走多远的一个圆圈 around origin, your work is still 2 pi. 不管是大还是小，不管是大还是小，你绕一圈 origin 你就是2 pi 的 work done。不管你在15那边绕一圈，还是在0附近绕一圈，都是2 pi。OK， OK 吗？ This is what we have proven just now. OK， any question？ 有问题吗？ Okay. So actually we have bring out an idea of rotation now. 有一个 idea of rotation. Because when we do loops, right, well, our wood done is naturally rotating. Okay, 是在转的。So, 我看一下要不要我们进一个 definition，我们再 take a break. So, actually, how we get the del Q over del X minus del P over del Y is from this operation here, what we call a curl F. curl F, curl 是什么？还有没有这边女生喜欢去卷头发？还是男生也喜欢卷？其实有些男生不是会按那个离子烫的，对吧？你是天然的还是烫出来的？你是天然的哈 ，OK， 好。有些人会去烫头发嘛 ，OK，curl，所以他去卷，他会卷啊，对，懂吗？啊，没有啊，爱美是天生的，对不对？是天生的 ，OK 的。哎，川也是烫出来还是天然的？烫的是不是？所以烫了会磕嘛，会卷嘛 ，OK， 会卷。So we want to check 这个 vector field 多卷，这个会有多卷 ，OK，curl of F。So what's how do we check 这个 curl of F 有多么卷？它是向外卷还是向内卷？Right. So how do we do this? We take cross product between the this one. This is what the gradient vector here. Okay, gradient vector. Oh, that's right. So write it down here. So this operator here is called gradient vector here. Where gradient vector function. You take cross product with f. Okay, cross product with f. So you can see that 大家会看这个东西吗？你们会看这个吗？ Okay. Okay. So what you do is you take the first row. Yeah, take the first row and then you multiply in a opposite, in a cross manner, and then you will get the third component. Yeah. Okay, so let's see how we get the curl on my Green's theorem here. So if my F is just consisting two component, right? So F1, F2, the third one is 0, okay? You can see that if you do this crossing here, or if you do this crossing, what do you get? So let's say del X, del Y, and del Z, okay? But my F3 component is 0, okay? So what do you get? You recognize? What do you left with? Oh, I think in the Z direction, we also need to be 0. There's no change in Z. Okay. What happened? Huh? So you only left with the third term here. Okay. So this is the del Q over del X minus del P over del Y here. Because we set the dx part to P and then set the Qx part to, dy part to Q. Okay. So actually what you are computing is you do work around the closed loop. You are computing the multiple integral for this curl F here. The curl of your vector field. How curl is your how curly. Okay, later we'll return to curl again. We'll see curl in a higher dimensional space. Okay. Yeah, so let's take a break again until 11:03. OK，什么时候要讲？我定一个时间，可能应该会在 week 16，是半夜还是半夜？
一个
那个哎，什么？这一个是不是可能会一百个 Q？这是不是？出不了。哦，它不是嘛，对不对？因为它有一个 close，它不是零，这样它就不可能变成零。所以不知道对于每一个 close loop，它都要100进去。每一个。这一个条件是每一个 close loop，每一个，不管是怎样，要一个人去的。好，现在我们找到一种，它不一个人。
这一个
在题目上，这个是最麻烦的。只要你的 close loop 包着一个 origin， 但是它的
有点口错。
这其实那边没那么难。
这也不是你错了，是他们他们家就回去了。回去是算他们的有些事情。
怎么会选这个礼拜回去哦？因为圣诞节不回来了，还是圣诞节也不在啊？应该有回来。OK。
你要停下来就讲说，我们交流，当时
点啊，
哎，你们有没有人玩 Clash Royale？
有。
对，背包连赢20次了。
哎，不能，
哎，但是
连赢24分。
我要那个东西。
连赢24分，连赢24分。
我拿到那个东西，
看运气啊。
看运气。我今天没有，我现在是你可以自玩，
这样子你就
随意的。
对，你输，我通常是一输一保就玩，整天没玩。
啊 ，game 都是这样子的，你
输了一次，你输一次，你输了就玩了。啊，你赢过，你继续玩。玩到你每天说不是，我到10单啊，不能给你赢啊，但是那个东西它就不一定，手臂这样上，一输就不要玩，然后
这个情绪，
拿送给你。
我要拿到那个第18次的。哎呀，老师帮你这样说，你帮孩子会死啊！
是玩不到。对， 哦，
乘以24，我俩要玩一个钟。
其实
其实不用一个钟也可以，如果你打得快，
我想到那个是容易啦，
对啊，没有啦，我不讲。
这个，
对，我确实会这样。
我跟你死了吗？
现在我那个，我觉得我现在金钱啊，你可以无限玩。哦，只要你对对。
那个我要按我的那个
我以为可以连着玩啊，scam 我，所以我才买了这个东西。但是输完3次你就 reset 了。对啊，我还以为是连着，你知道吗？
分辨到路上
啊，
以前这样，
我没有注意到，
不能输3次，输3次输3次
就 reset。
16，我是16，
我知道第16，
我第18还好，16个又不，
发的也不错了。
上网找攻略啊，
没有找到，我是个人，
是跟人打，那个是跟人打。哎，我怀疑啊，如果我赢太多次，他会不会拿一个直接
我记得
没有，可能输太多次会，输太多次会，
他会配一个，给，会你还匹配一个比他的牌比你好，直接考试你的牌，
对啊，
考特。
对啊，
一些人一般让自己干，你很喜欢玩，你进去的，玩的其实是你是很难所以
哦是啊，
我不其他人家打给这个这样
是啊，是拿不到指定哦。
你看那种很智障的，就很会玩，让你讲任何东西啊，很智障的，不会讲话之类的，很身体的。
会下次啊，这次不是你下次是哪一个？
可是这是我金钱。我以为是可以连着，然后后来发现不能，不能。啊，没有没有，它就是 for 这个月。对，我也是前面的。练完还是？
那你要讲3个小时有赢不掉，
我那个跑一直跑，你看他跑没有不懂。
你在讲他玩，
我连跑步不成，
对，排名啊，很劲啊。
爽，我在搞爽。
都这个。哎呀，我真玩，我还在上面天上。我那个地方没接啊，对啊，他笑
八练的，
他就笑你，他那个不接了，
刚好你的八练刚好用可以用到我八练。
他就笑你讲，那忘记在这里面。
有的人就是很，我就特别忘记了这个事情，
所以我真的忘记了。
你真的忘记了。
Okay, okay, so Okay. I'm gonna start last hour. Um, so let's try and compute one curve examples here. So one thing you notice here, curl of a vector field, you still get a vector field. Okay, because you cross two product, you get a sorry, 我在讲嘛 you cross two vectors, you still get a vector. Okay, so let's try and compute this curl of this vector field here. In the meantime, you compute, I try and plot out these two vector field for you to see about the curl and the vector field itself. Okay, try and compute the curl of this function vector field. Try and plot a vector field for you. Quite quiet. Yeah, so what did you compute? So did you get negative 9xyz squared, comma negative x2x plus x squared y 3yz cubed minus x squared z. Do you get this? Okay. Okay, so I tried to plot out this vector field here. Okay, so you can see that this vector field, what happened? It's like rotating, but it's like the, can I say tornado? Because on one side is going down, down. Yeah, on this side is going down, on here is going up. Kind of like a tornado. Is it a tornado? Yeah. So on this upper, so on the other, on this half of plane, so where's this half of plane is it? So on the negative side of y, it is going up, and then on the positive side of y is going down. And going down. Okay, so 螺旋 rotating vector field here. 等于什么？它的移动吗？哈？ Oh, not quite, not quite. It's just rotating. 没有上下. It's just rotating. But you can see that the vector that is further from the origin is longer. 比较长，对不对？比较靠近 origin 呢就比较多。如果 if you stay away from the origin, you get pushed further. If you stay closer to the origin, it get pushed shorter. Okay, so you can see that there's a non-trivial curve here. So the idea of curve. All right, let's see. But somehow I cannot plot this curve out. Very weird. Don't know why. Trying to plot the curve vector field, but doesn't work. Maybe you can try and plot out the curve f also. See what does the curve f do. Okay, so let's go to the next one. So next theorem is a curve of a del f is 0. All right. So just now, Yixian asked a question, right? Whether this vector field is a conservative one or not. What do you think? If it is a conservative vector field, meaning what? You need to find it as a gradient of a scalar field. Okay. But there are three equivalent definition, right? Or statement. Okay, so if you check that, this vector field has what? Zero integral. When you integrate over all loops, then it is conservative. But I already produced you a closed loop, which is such that the integral is not 0. It is 2 pi. So meaning this vector field is not conservative. Okay. Yeah. Okay. Because there exists a closed path such that the integral is not 0. So it's not conservative. Because to be conservative, you need to be 0. Okay. If you integrate over all closed path. Right. So how to prove this curve of a del f is 0? Well, I mean, 这种题目怎么算呢？就算咯，算左边咯，把它开出来，左边是什么东西 ？Okay, open out the left hand side. So what is the left hand side be? So let's apply the definition. Okay, so well, you apply the definition ijk here. Okay, and then this is what equals to the gradient vector cross with your del f. So gradient vector cross with del f. So what is gradient vector here? Del over del x, del over del y, and then del over del z. But what is gradient applied on f already? So meaning you have del f del x, del f del y, and del f del z. Okay, yeah. So you do cross product between these two vectors. So what do you get? You get a bunch of second derivative. or second partial derivative, which we call the mixed derivative here. Okay, so you get a bunch of mixed derivative. So what did you observe here? What did you observe here? Claira's theorem. So you can see that they differentiate with a different order of variable here. Just swap order, but what? But the sign is different. Okay, so there's opposite sign inside the sum here. Okay, Claira's theorem says what? Claira's theorem says that it doesn't matter you differentiate by changing the order. Okay, 还记得吗? Like del x del y f equals to del y del x f. Okay, by okay, yeah. So Fubini tells you integration, you can change order. Claira's theorem tells you you can differentiate by changing the theorem. Okay. Sorry, by changing the order. Okay. OK 了 ，OK 吗？有问题吗？问题吗 ？Okay, so right, so curl of a del f is automatically 0. So let's see what happens to this curl here. So you can see that if your curl is 0, then if your curl is 0, meaning your vector field is not doing a rotating work here. Okay, it's not doing a rotating work. If you compute that the curl is non-zero, that means your vector field is somehow rotating. Okay, it's somehow rotating. Okay, no. Okay, so you can see that if your vector field is not doing rotating work here, your curl is typically 0. Okay, and then positive curl meaning your work is in the positive direction, counterclockwise. So if your curl is negative, okay, you will see that your work is done in a clockwise orientation. Okay, 可以吗？这只是一个总结吧，我没有 proof 给你看为什么它对。Okay. Okay. So what? So let's say, let me ask you a question. So question here. What if f is conservative? Okay. Curl f equals to what? 0. Why? Since f will be equals to a gradient of some scalar function, but we just proved that this number is always 0. Okay, so if is a vector field is conservative, then the curl of f is 0. Okay, 它没有在做一个 rotating 的 work. Does it make sense? Okay, it's not rotating. All right, so we have obtained a theorem here. 你 prove 了一个 theorem. So if f is a conservative vector field, then curl f is 0. Okay. And the converse is almost true. Okay, the converse is almost true. But we have a condition on vector field, which is the vector field you start with have to has continuous partial derivative first. And then if the curl f is 0, then f is a conservative vector field. So we obtain another way to check whether a vector field is conservative or not. And then this way is the one that I told you last time. Okay, the weird combination of equation that you need to check. Okay, so those equations are coming from this curl condition here. So let me show you. Should we show it? Let's show it. Yeah, let's show it. So well. So let me bring down the condition that we had last time. 在哪里？在这里。This one. Okay. Last time you asked like why so weird one these thing, where these come from. So let me bring it down here. Okay. So where this come from? Where these three things come from? Okay, where these three things come from here. So if you compute the curl of f, what's the curl of f again? So curl of f is defined as what? So let's bring this calculation down. Paste here. Okay. Okay, so you can see that curl of f is 3-component vector field here. But if you set this vector field to 0, it's exactly the equation we are checking last time. Set this curl f to 0. So if we set this to 0, this is the exact thing we checked last time. Okay, so actually last time what we checking is you are checking that curl f is 0. So where this thing pops up is because of the curve. So f is conservative if and only if the curl of f is 0. But remember, one direction is true because of the curl of del gradient of nebula f is 0. But the other direction you need this condition here, continuous first partial derivative. So f1, f2, f3 has to have the continuous first partial derivative so that you can get from the direction if curl f is 0 implies that f is conservative. We didn't prove it to you, but you need to be aware about this condition. Okay, I mean it makes sense, right? Does it make sense? 为什么我们讲那个 f1, f2, f3 have to have continuous first order partial derivative? Why? Because you need to compute these things. You compute these things. It's a first partial derivative. Yeah. Now just solve. And then you need to show that you can kind of integrate. Okay, 对吗？要 integrate 回去. I mean, you need to find the f. You need to find the f, right? You need to find the f such that the gradient of f is this capital F here. So to find this f, you need to kind of integrate, right? Integrate this capital F here. 对吗？你要 integrate 这个大 F 啊什么？你要找 gradient F 什么？再讲一次。So okay, so this line says that the gradient of this scalar field is this vector field, right? Okay, so you are 你要找这个小 f 要怎样找啊？就是你要做类似 integration 的东西哦。So if you want to integrate these partial derivative, right, then 你就要 have continuous the condition. Okay. All right. So let's check this. So determine whether this vector field is conservative or not. So how to determine this vector field is conservative or not? One way, I mean few ways. You check that the line integral is independent of path, or you check that the loop integral is always 0. Or the third way is to check the curve. Okay. If curl f is 0, that means this vector field is conservative. If curl f is non-zero, then this vector field is not conservative. Okay, so you just check curl f. 要 check 吗？还是你觉得很闷？会闷吗？还是你要 check？ 还是会算了吗？会算我们可以 skip 其实。You want to check or you want to skip？ 闷吗？算这种东西。可以 skip 啊 ？skip 啊 ？Okay. Okay, let's skip this. Okay, let's do this divergence. Divergence is a new concept here. Okay, so in this topic, curl and divergence. Okay, very important. So what's divergence here? So divergence here still play with same object. Also the gradient vector and vector field. But this time, instead of taking cross, you can take dot product. Okay. So what happens if you dot two vectors together? You will get a scalar. Okay, a number here. Okay, so once you dot gradient vector and the vector field together, you get a scalar function. Okay, just one number. But this number depends on the points or it becomes a function. Okay, scalar function. Okay, so let's do one example here. What's the divergence of this vector field here? Div H F is equals to the gradient vector dot with the vector field. So how to dot them together? So the gradient factor is del over del x, del over del y, and del over del z. Okay, and then you dot with a vector field x squared y z, comma 3xyz cubed, comma x squared minus x squared. Okay, so if you dot them together, can you quickly compute? You get 2xyz plus 3xz cubed minus 2z. 看一下有没有拿到这个。Let me see if I can plot this vector field for you. Oh, actually it's the same, right? It's the same vector field we had just now. Okay, so do you get this? 有看到这个吗？ But 金生，你要不要问一下，这个不是号码来的？说这不是号码，他不是讲是应该是号码的。对，没有错。So this number will change at the point you look at. Okay, if you put in different point, it will show you different number here. So what does this number correspond to? If you check that this number is less than 0 around this point, it means that the vector field is going into this point. So this point usually we'll call it a sink. Okay, sink. Okay, and then if the divergence is greater than 0, meaning around that point the vector field is diverged. 就是发散的，就是出去，叫什么呢？ We call it a source. OK， 就是你是那个源头嘛，你源头你有货，你一定发出去了嘛。OK， so source. And then if it's 0 means what? 没有进没有出。No, meaning the rate of going in and going out is the same. 不一定是没有进没有出，但是 the rate is the same. 进出的rate is the same. But the rate of going out and in is the same. 对吧？你看，它又有进去又有出来，不一定是没有没有进没有出。OK， 这个东西没有名字吧？没有名字。S 开头是什么？Well, I mean 不懂哎，这个不懂，这我不知道，吧好像没有名字。OK， so yeah， OK， 这个是 about divergence， 还有半个钟。Okay, let's quickly go through this section here, parametric surface. 这个不是特别重要，不是特别重要，就是 I mean, this is a tool we're gonna use to do integration, but we won't focus on building this parameterized surface. So let's quickly go through. So what's the generalization of parametric surface? Actually, this comes from the parametric curve. Okay, so in parametric curve, so what you do is you look at RT only. You get RT, and then you have XT, YT, and ZT. Okay, YT and ZT. But in this case here, you are parameterizing a surface, so you need two variable. Okay, so you need two variable. So your R takes two variable now, for U and V. Okay, and then each two variable give you a point in 3D. So you have XUV, YUV, and ZUV. Okay, I think this is the one that Huiqi did right in your project too. So you are actually doing a parameterized surface. Again, not line anymore, not curve anymore. It's two-dimensional. Okay, so you need to take in two variable here. So what's the 有什么好处啊? What's the nice thing about doing this? Is geometrically you are taking a surface in R2 and then you put it on R3. Okay, you put it on R3. 比如说啊，我把这个椅子不是这块布我剪下来，放平平的，它就是 2D。But 你把它贴上来 is a parameterized surface already. 它有高度啊。It has height now. Okay, 这个皮啊，这层皮不是它有高度啊，对不对？ Okay, so we parameterize this surface. Okay 吗 ？Okay， 我们把一个平面东西让它有高度。Okay, so let's quickly go through. No need to copy. So let's say we want to describe this surface here. So can you imagine that this cylinder is coming from a surface? 可以想象吗？它是从什么 surface 来的？这个 cylinder， 它是从什么 surface 来啊 ？Sorry， 不应该这样讲，从什么 surface on the plane 来的 ？OK， on the XY plane， 你觉得呢？啊，蛇哥，不然你贴给我看一下蛇哥怎样贴出它。多个蛇哥，你的切法是这样切是吧？ But now I want to discuss how you take a surface in R2 to build this cylinder here. What do? Actually, you are taking a plane, 对吗？你是拿一个 plane 把它贴起来。来，我拿一个纸，对。No, you take a plane, right? And then you how to say? You 怎样讲啊？卷起来啊，怎样卷啊？卷怎么卷的？也不是 flip 啊，我本来讲 flip， 但是不是 flip。You I mean you glue two sides of your plane together, you will get this cylinder. Okay, so you can see that. Okay, you see so you can see that where can I take this UV so where's the two variable here? Okay, so 看一下 two variable 在哪里。So you can see that here is U, and then one of them is V. Okay, how do you recognize that this is a cylinder? 怎么 recognize this is a cylinder? First of all, 看到 cos U 又看到 sin U， 然后看到他们两个前面又是一样的号码，你不会很想做一件事情吗？你不是觉得你很想做一件事情吗 ？R cos U R sin U， 它符合什么条件？R sin I mean 2 cos U 2 sin U, they satisfy what equation? Circle equation with what radius? 2. Okay, radius 2. So how do you form this circle? You use what to form circle? S coordinate and Z coordinate. So in the X Yeah. In the XZ plane, you have circle. Okay, in XZ plane you have circle. Okay, no, 对吗？看一下这个图是不是 XZ plane 有个 circle。Okay, centered origin with radius 2. Then how do you get all the other circle here? You look at the y direction. What happened to the y direction? There's no u there. Instead, what you have? A v. And v is an independent variable. Okay, v doesn't affect the other two coordinates. So in the y direction, in all the y direction, you will just have the circle of radius 2. Okay, so that's how you get the cylinder. Okay. So how do you form this cylinder actually? How do you form this cylinder? What's the plane that I'm talking about just now? What's the plane you can take? So let's say here is U, here is V. So what's the plane I can take here to form the cylinder? V 要从哪里拿到哪里才可以拿到下面这个 cylinder？ minus infinity to infinity. Okay, so you have a infinite strip here, 无限长的 strip. But how about U? To form the circle, what U you need to take? So V from negative infinity to infinity, and then U you take from 0 to 2 pi. Okay, so this strip is where this strip lies. So your strip lies on 0 to 2 pi, and then you take this infinite strip here. Okay, infinite strip. Okay. So you got 0 to 2 pi. Okay, 0 to 2 pi, and then you go infinite on one direction. So you just glue the side on 0 and 2 pi to them. Okay. Obviously you can take more than 0 to 2 pi. 是吗？你可以拿多嘛？ You can take more, right? You can take more if you like, but you just repeat your circle a few times. Wrap your circle a few times. I mean the cylinder, yeah. Okay. Okay, so this idea is very important. How to go from a plane to a parametrized surface. 所以你全部你这些 surface 都是用一块大布剪出来的，对，都是用一块大布剪出来的，对吧？ Yeah. 你看柯灯就是一块大布，你摆平它就是一个灯上面的一片布。Okay. Again, 看一下还有其他的 surfaces. Let's look at this surface. So this is a plane. So so this plane, instead of giving you the normal vector, right? It gives you two non-parallel vector A and B. Okay. This two vector here. So that pass through a point P. So now you want to parameterize this surface here. So to parameterize this surface, right? You need, what do you need? So what's the thing you need to parameterize surface? RUV equals to XUV, and then YUV, and then ZUV. Okay, so you need to tell me these three functions here. How to tell, huh? How to tell, kind of difficult. How to tell? What do you think? How to tell here? So, well, you need to tell me on this plane, right? How the x coordinate depend on UV, how the y coordinate depend on UV, and then how the z coordinate depend on UV. Okay, so what's the UV we need to fix here? What's the UV we need to fix here? What's the UV we need to fix here? So there's some hint given by this question here. So there's some hint given by this picture here. if you have a B, you have a A, okay, and you can consider a scalar multiple of B and A. Okay, scalar multiple of B and A. And you should imagine that how to get everything inside this plane here. You can take linear combination of B and A. Okay, you can take linear combination of B and A. Okay, yeah. So 知道这些又怎样？怎么写出来？就这样发吗？什么？这是在2D 还是3D 哈？这是在3D，这是在3D，because this is a parameterized surface。这是个3D。So meaning what? These vector actually live in R3。这些点都是在 R3 里面。怎么形容里面的点呢？怎么形容里面的点呢？怎样形容里面的点呢？Well, okay. So every point in this P naught here, let's call it P. Okay, let's call it P here. So how to get a vector from P to P naught? Okay. So just now I say that this vector should be a linear combination of B and A. Okay, linear combination of B and A. So you can write that the vector P naught to P as a linear combination from with A and B. So whenever we say linear combination, linear combination we will say over what? Over what number? So what's the coefficient you can multiply? So here is over R. Okay, so this U and V should be over R. So U and V over R. Okay, over R here. Okay, so this is a vector. But this implies what? Okay, so this implies that we can write that every point. Okay, so here. So we can write that every point on this plane, okay, to be what? To be the fixed point x naught, y naught, z naught, plus the linear combination of the vector a and b. That's all. 就这样吧。Okay, yeah, 就这样。Why there's a p naught here? Because usually we will start with the origin, right? Okay, but this time we can start differently. We can shift the origin. Okay, we can shift the origin to anywhere. Okay, in particular, S not Y not Z. Yeah, 有问题吗? So the main point here is you want to realize every point in the plane as a linear combination of two non-parallel vector. Okay, if they are parallel, then that means what? If they are parallel, huh? Yeah, if they are parallel, they're just two different lines. Even if you add them together, it will just form like maybe different line. You won't get any point in between these lines. Okay. How about sphere? Okay, let's look at sphere here. Sphere may be a bit interesting. So if you look at this sphere here, so this sphere here is a sphere centered at the origin with radius a. Okay, so if you write down the spherical coordinate, this is what we learned before. But now you can see that this sphere is actually a surface, right? Okay, because if you cut the sphere and then you light it up, it's just a surface. Okay, it's just a plane. It's just a surface in the plane. So what do we mean by we cut it up? So how we cut it up? So how do we cut here? So in spherical coordinate, how many variable? 3 variable, right? Radius, theta, and phi. Okay, theta is the one on xy plane, phi is the one on z, the angle from z axis, positive z axis. But here, in this sphere here, one of the variable already fixed, which is the radius. So only theta and phi is changing here. So to get the whole radius, what do you need? You need theta from 0 to 2 pi, and then phi from 0 to pi. That's all. Okay. So this is the plane this is the surface on the plane that you need. So this is a finite strip. Okay. Yeah. Okay, ma. Okay. So this is the finite strip you need. 可以想象怎样从这个 strip 粘到这个 sphere 吗？能够想象吗？想得到吗？怎样粘？记得的还是这 OK， 能想象怎么粘吗？Maybe we go over these examples. We can finish today's work. Maybe 2 more to go, then we can finish today's. 可以想象怎样粘吗？你不能想象怎样粘 ，at least 你去找一下这些点在哪里，这些 boundary point 在哪里？在哪里啊 ？Origin, let's say this origin here， 它在 sphere 的哪一个部分？啊 ？So this origin means what? Theta equals 0, phi equals 0. Okay, so theta equals 0, phi equals to 0 should be the North Pole or South Pole? North Pole, right? Because phi equals 0, ma. Phi count from where? From positive z-axis. Okay, so this is the correspond to the 0 point here. And then, how about this point here? This is a point 0, 2 pi. Or not? Okay, so phi is still 0. And then theta is 2 pi. Should go to the same point. Okay. How about this point here? Pi 2 pi. Phi is pi, meaning you have to go all the way down to South Pole. Okay, so pi and 2 pi will correspond to the South Pole. And then this point also correspond to the South Pole. 这4个点都知道，要不要知道一下那些线跑到哪里去？旁边这些线跑到哪里去？ Okay, what did you notice here? Along the first vertical line here, joining 0, 0 and 0, 2 pi, all the phi should be 0. 我全部还是在这里点。And then the angle is the whole circle here. So 这条线好像整条都送去 North Pole, right? Every point in this line gets sent to North Pole. Similarly, every point on this line gets sent to South Pole. Okay, so vertical line 我们解决了。Horizontal line 呢？ How about horizontal line joining 0 to pi here? 这样想啊。So horizontal line here, the theta is still 0. Okay, theta 0 means what? Meaning it is at the positive x-axis. Okay, and then phi is going from 0 to pi. Okay, so meaning this part here, positive z-axis, and then phi is going from 0 to pi. Okay, so let's plot it out. This direction, hey, let's use this color. This direction here, we got this line here. Okay, how about the other side? How about this side here? Okay, this side has what? Theta equals to 2 pi. Okay, theta equals 2 pi. Theta equals to 2 pi is the same as 0, right? You go 1 round already, 回来了. Okay, so your red line here also sent to this line. Okay, so you can 想象怎样粘了吧这个东西 上面两个点上去，I mean 上面那整条线上去。I mean well, okay，再用这条东西。Well, I mean, let me see 啊，所以，two vertical lines can send to a same point，所以你要想象要把这边变成一个点，这边也变成一个点，连起来了。那下面这两条怎样呢？把它卷起来，卷起来 ，but these two side 送去来不同点 ，right？把它拼在一起哦，这个就是一个 sphere，就是这个 sphere。因为它有折了，所以它被折了，所以它不够圆。对，I mean 这边被包起来，这边被包起来，这就是一个圆。好的，世界地图，世界地图一样，世界地图也是这样。OK，可以吗？几点了？50分了。我看一下。OK， 快讲过这些。So, you also can parameterize cylinder, paraboloid, and this was the surface here. 最后一个不知道什么 surface 来的。Okay, so you can try these surfaces. And this parameterization is not unique. It's not unique. Okay, like curve, you can make the speed faster, or you can shift it by changing the domain also. Okay, yeah. All right, so we will continue next lecture, the final lecture. We'll finish up divergence theorem, Stokes theorem. And then maybe I can tell you something about exact differential equation. Okay, so see you next week.